Hi, let us talk about the concept of under-reinforced concrete beam. This is one of the important concepts in the design of reinforced concrete beam. As you know, concrete is weak in tension but good in compression. Reinforcements are provided in the concrete in order to strengthen the concrete, taking the tensile stress so that the reinforced concrete member is strong in both tension and compressions. Now, depending on the amount of reinforcement provided in the member, the levels of reinforcement shall govern the response and the behavior of the member. There are three main types: over-reinforced beam, balanced, and under-reinforced beam. As implied by the terminologies here, over-reinforced beam means that you have plenty of reinforcement, surpassing what is necessarily needed. As for the under-reinforced beam, the amount of reinforcement is insufficient as compared to what it is required. As for the balanced reinforced beam, that means the amount of reinforcement is at the break-even point, where the amount is provided is just nice to meet the capacity of the concrete. Now, many students are confused with these three, having the misconception that over-reinforced beam is preferred. This is not true. Instead, when we design a reinforced concrete beam, we would like to make it under-reinforced. Why is it so? You can imagine a reinforced concrete beam in this manner. There is a weight here. This represents the stress within the reinforced concrete beam. This weight is carried by two persons here. The first person is the steel. The second person is the concrete. These two persons have two different behavior when they are overloaded. Now, when the steel is overloaded, it gives a ductile behavior. This person will inform you that I am about to fail. You need to be careful before he actually fails. As for the concrete, this person is more silent. He will bear with the load without any complaints until he fails suddenly. This represents the brittle failure. To make it simple, the task here is to ensure the weight is being lifted. As long as the weight is off the ground, the member will still last. Now you are increasing the weight gradually until either one of these two fails. Now, which do you prefer? Do you prefer the steel to fail first, or you prefer the concrete to fail first? In the reinforced concrete design, we don't like brittle failure, as it does not give us warning prior to failure. Now, in the case of overloading, we do not have sufficient time to respond to the failure. Therefore, for the survival purposes, we want the members to fail in ductile. Now, how do we correlate this with different types of reinforced concrete beam? Now, a balanced member happens when both the steel and the concrete fails together. They are about the same strength. By the time the member fails, both will fail together. As for the over-reinforced member, the steel is stronger. Under no circumstances, the steel will fail, and in the case of overloading, the concrete will fail. This kind of failure is normally due to crushing at the high compressive regions. You know that the failure of the concrete, it will be brittle. There won't be any warning signs. So, this kind of failure is supposed to be avoided. Next, we talk about the under-reinforced concrete. This time, the steel is weaker. The amount of reinforcement provided is insufficient. Therefore, in the case of overloading, it will always fail at the steel. Now, before failure, this person still will notify you that he is about to fail. This gives a ductile response, and this kind of failure is preferred. How do we know that the member is about to fail? You will see significant elongations of the steel as a result of significant deformations of the beam. This triggers the cracks on the surface of the beam. By looking at the cracks, densities of the crack width, crack length, and the locations of the crack, we will know that the member is about to fail. Having this understood, now you know that when we want to design a member, we will need to always ensure that the reinforced concrete beam is under reinforced. Under no circumstances, we should allow the reinforced concrete beam to be over reinforced. Knowing this, how do we cater for this in our design? This is the next common questions asked by the students. As most of the students are not aware, these considerations has already been incorporated within the equations for the design of reinforced concrete beam. To explain this, let us first look at the stress block diagram here. You know that in the reinforced concrete beam section, there is a neutral axis, which is located at the distance x from the top of the beam. This neutral axis divides the compressive regions and detention regions. The concrete has the capacity to undergo compressions, while the steel are designed to take the tensile stress within the section. Now, this X here varies in accordance to the load applied onto the reinforced concrete beam. When the member is subjected to low loads, little deformations develop. This leads to very little compressive strength of the concrete and small X here, which result in small stress block to provide the compressive force. Now, reaching to the ultimate state, just before the concrete fails, the maximum allowable compressive strength of the concrete is 0.0035. This is set by Eurocode. At the same time, the neutral axis relocated, become further away from the top beam until reaching to a state the member enters the over reinforced conditions. We will need to prevent this. In order to prevent the members to be in the over reinforced state, we will have to set the maximum limit of the X here. How do we do that? First, we need to find the limit of the X. You can take the balance conditions as the reference, as this represents the break-even point. Assuming now the concrete strength and the steel strength reaching their capacity at the same time. Use the principles of the interpolations on the basis of the compatibility of the strengths. You get the relationship between the steel strength and the concrete strength. Epsilon st divided by this distance shall be equals to epsilon cc divided by the x. Now, what is this distance? It will be determined from d minus x. You get this distance. Rearrange the equation, you get this, and rearrange it, you get x equals to this. Now you substitute the limits for the steel and also the concrete. You will find x should be equals to 0.617d. This is the state where the steel yields and the concrete fails. Now you want the members to be always under reinforced. Therefore, theoretically, you will need to make sure the neutral axis will always be less than 0.617D. As a safety measure, Eurocode limit it to be 0.45D, which is less than 0.617D, which is the actual condition. So this is the way that Eurocode ensure that the reinforced concrete beam will always be under reinforced in order to secure a ductile failure. Now, if you look at the equations used for the design of reinforced concrete beam, you don't see the 0.45D. For example, the singly reinforced equations involve K, Z, and also AS. As for the doubly reinforced beam, it involves K, AS, and AS prime, and also Z. You might be wondering, where does this X less than 0.45D is being incorporated? First, it is incorporated in the checking of the K versus the K balance. K balance represents the balanced state, which by the definitions of the Eurocode, instead of the actual 0.617D, Eurocode limit it to be 0.45D. That gives the compressive force of the concrete at the balanced state to be equals to this. And the S here, which is this, is defined on the basis of the X equals to 0.45D. How do you work out the force of the concrete at the balanced state? You use this 0.567 FCK, multiply the S, multiply the B. And within the X here, you have an X, which is equals to 0.45D. When you equate this balanced state of the concrete versus the steel force, there will be a balanced amount of reinforcement. Rearrange the equations, you get this. Now you know how Eurocodes prevent the members to be over reinforced. In the design of reinforced concrete beam, there will be always a step checking for the maximum steel area in the member. If the amount of reinforcement exceeds that, you will have to redesign the section. You cannot use the section because later the sections it will be over reinforced and ductile behavior cannot be ensured. Bear in mind that the maximum amount of reinforcement is worked out on the basis of the conservative value of 0.45D. Let's say even though you are using 0.5D, as long as it is less than 0.617D, you will still expect the members to fail in brittle. This is the conservative measures of the Eurocode. Now, you might want to ask, what happens if you really need that amount of reinforcement in the member? And when the maximum steel areas has achieved, any countermeasures to be done? Yes, the sections will transform from the singly reinforced sections into a doubly reinforced section. To make it simple, you may also observe from this example. You know the singly reinforced member, you have two persons, steel on one side, concrete on the other side. And the weight here comprises two parts, the tension and the compression. In a typical singly reinforced member, the tension is fully taken by the steel, while the compression is fully taken by the concrete. Now, what if the steel is over reinforced? Under such circumstances, there is no chance that this person will fail first when the member is overloaded. In order to prevent this, the concrete will require a helper taking the compressive stress. If one person cannot outperform the other, you have two persons to compete against the steel here. This will be the compressive steel, which are this. When the compression steel is embedded in the concrete section, it also helps to resist the compressive force. By adding up the strength of these two persons here, now these persons become weaker. Therefore, in the case of overloading, this person will always fail first, and this will give us ductile failure, which is what we prefer to have in the reinforced concrete member under the ultimate states. Now, if you observe these two scenarios here, you can see the differences between the singly and doubly reinforced member. To make it simple, when the cross sections is relatively large as compared to the load acting on it, normally we can design as the singly reinforced member. Now, when the member is subjected to large load and the cross sections of the member is relatively small as compared to the load acting on it, you will need stronger steel to resist the load, and this can easily lead to over-reinforced state. Now, in order to ensure that the failure always occurs at the tensile reinforcement for the ductile response, the concrete here will need an additional helper. This is when the compression steel come into function. Now the next question, what is this relevant to the x equals to 0.45D? You know x equals to 0.45D is the numbers limit by EC2, so that the members always fail in the ductile failure. Now the moment resistance of the concrete member, it will be due to the tensile force of the steel times the lever arm. This lever arm here, it will be on the basis of 0.45D. How specifically it is being worked out? You can work out graphically. When the x is equals to 0.45D, the z balance here, it will be from the centroid of the tensile reinforcement to the center of the stress block diagram, which is half of the height of the S, as expressed in the function here, which ultimately it will be equals to 0.82D. Now, if you look at the list of the equation here, when it comes to the z here, we will always use 0.82D for the doubly reinforced member. And then there is a control here for us to determine whether to use singly reinforced member or doubly reinforced member. There is a limit of the K, which is known as the K balance. K balance is worked on the basis of the 0.45D, as indicated by this equation. To determine the K balance, you will need to first determine the M balance, the moment capacity of a singly reinforced member when it reaches to the break-even point, which shall be equals to the force of the concrete at the balance state multiply the Z at the balance state. Z at the balance state is worked on the basis of 0.45D. As for the force of concrete at the balance state, is also worked on the basis of 0.45D, which is this one. Now the moment acquired here, it will be also on the basis of 0.45D. Rearrange this, you get this, and this whole thing represents the care balance. Now you have a better understanding of the flowchart of the equations for the singly reinforced and doubly reinforced member. And if you avoid to all these design equations, both singly reinforced and doubly reinforced member will always fail in ductile manner. Let us go through this one by one. First, you need to determine the K based on the moment acting onto the member. If the moment relative to the cross-sectional area of the section is small, which is smaller than K balance, which is equals to 0.167, now you can go for singly reinforced member. Since the K is always less than the K balance, that means the X will always be less than 0.45D. Under such circumstances, the sections will always be under reinforced. You will expect the steel will yield before the crushings of the concrete. Now let's say your moment is relatively large as compared to the cross-sectional area of the concrete. That the K now exceed the K balance equals to 0.167. You are entering a state where the steel reinforcement will be larger than what can be taken by the concrete. In this case, you need additional compression steel to help the concrete on the compression part. Having these two persons stronger than one person here, in the case that the member is overloaded, the failure will always happen at the tensile steel. This will still give you the ductile failure. Now, having the K balance to control whether you are using singly or doubly reinforced member, you know that singly reinforced members will always be under reinforced, and double reinforced member has the risk of over reinforced. Now you need additional reinforcement bar, which is the compression steel bar, in order to strengthen what is able to be resisted by the concrete. And this part here represents the limits of the singly reinforced member. To make it simple, this part represents the largest strength can be given by this person here. As for the compression steel bar, it will lead to additional compressive strength so that the collective of both to be stronger than the tensile steel here. And then when come to the K balance and the Z, everything will have to work on the basis of 0.45D. As you can see, we want to ensure that reinforced concrete beams is always under reinforced, so that the member fail ductilely, giving us warning in the case of overloading, so that responsive actions can be made quickly before the actual failure of the member. This is achieved by ensuring the X is always less than 0.45D as defined by the Eurocode. The differences between these limits from the actual 0.617D, it will be the safety precautions given by the Eurocode. And then the following derivations shall be worked out on the basis of 0.45D in order to determine whether the member is singly reinforced and doubly reinforced. That is the first one. As for the second one, those values shall also be used in the doubly reinforced members in order to ensure the under reinforced state. And then in the calculations, we will need to also check for the maximum amount of steel reinforcement, especially under the singly reinforced section, in order to prevent the steels to be much more stronger than the concrete.